All right. Thanks everyone for joining us in String Fino Seminar Series. Today, we're very happy to have Andreas Schachner from Cornell and LMU. He'll tell us about effective potentials, warping, and implications for f-time uplifting. Take it away.
Okay, thanks a lot. Let me start by thanking Menki and Mutu for the kind invitation to give my talk here today. And I want to talk about effective potentials, warping, and implications for f-time uplifting, which is based on work with Arthur Hebeker, Severin List, and Simon Schreier. And so the setting for our work are Type IIB flux compactifications. And in that context, there's a well-known solution as formulated by GKP in terms of so-called ISD fluxes, which is quite well understood. But this is just a single on-shell solution of the equations of motion. So that gives us a solution at a single point in moduli space. And quite famously, going off-shell in such setups is quite hard. However, there has been tremendous progress in the past expanding around these so-called ISD solutions and understanding locally the off-shell prescription of these types of compactifications. But the motivation for our work is slightly different. Namely, we were interested in understanding what happens if you turn on so-called non-ISD or AISD flux. And here the motivation is potential applications to the construction of de Sitter vacua from f-time uplifting as proposed by Saltman and Silverstein in 2004. So the idea is that you have an ADS minimums for the Kähler moduli and then a positive contribution from the non-ISD fluxes that can potentially uplift your potential to the de Sitter minimum. And so today, I want to illustrate a procedure on how to compute the f-shell potential in such background with AISD flux and estimate potential corrections parametrically. Let me also emphasize that in the past, other collaborations have looked into computations of such effective potentials, such as in hyperbolic compactifications of M theory, as studied by Bruno De Luca, Silverstein, and Doroba in 21. Good. So the starting point for our analysis is the 10-dimensional formulation of Type IIB. And we want to compactify that theory on a warp background as shown here. And we can then also pick suitable conventions for our fields. So for, in particular, the 5 form and the 3 form, where we then define fields phi plus minus as a linear combination of the warp factor and the 5 form scalar, the ISD and AISD component of the 3 form, plus an additional linear combination of these fields. One can then compute the equations of motion. I'm not going to go into the details here. You can see, for example, this paper by Liam for a bit more background. And you see that these equations are vastly complicated, and it's unclear how to construct solutions in general. But famously, if you just set sufficiently many terms in these expressions to 0, you can hope to find a solution. And this is precisely what GKP did in their famous paper. Namely, if you set all of these terms to 0, you can show that these equations of motions actually collapse to a Poisson-like equation for the warp factor, as given by this expression here. And noteworthy in this context is that the condition that the AISD component of the flux vanishes, this is actually a condition on the complex structure moduli of your background Calabi-Yau. So this fixes for you the complex structure moduli in this background. And it has been shown by GKP that in the 4D effective theory, these solutions are in one-to-one correspondence to solutions of the corresponding f-term conditions for the Gukov-Waffer-Witten superpotential. There's one important remark that I want to make here, namely, one notices that from the 10-dimensional point of view, the equation that you solve is actually independent of the warp factor, because the Hodge star of the Calabi-Yau acting on the 3 form is actually independent of any conformal factor. And so it's unclear as to how this is realized from a 4D point of view, but this is something that I wanted to highlight here and that I will comment on later on in my talk. But as I said in the beginning, we are interested in solutions that go beyond GKP, where we have AISD flux turned on. And to do so, we are proposing a scheme using solving the equations of motion perturbatively. The way we do that is as follows. So first, recall that the object phi plus to the -1 related to the warp factor, there's actually an integration constant that remains unfixed at the level of the equations of motion because it's just a Poisson-like equation, so you can just shift it by a constant. And this integration constant can be identified with the volume modulus. And this volume modulus we use to set up our perturbative expansion. So we expand all of our fields, psi, where psi can be either phi plus minus, the metric, g plus minus, or tau, in powers of 1 over c, plug that into the equations of motion, and then derive the equations of motion to each order in this expansion for each of these expansion coefficients. Okay.
Andreas, can I just ask you a quick question? Are you starting from a supersymmetric solution or a generic non-supersymmetric flux?
Generic non-supersymmetric flux. I will get to that actually now on the next slide.
Okay, thank you.
That will set for you the leading order background, if you wish. Yeah. So at the lowest order, the equations of motion are solved for phi plus 0 and phi minus being constants, and we choose these values here. Tau 0 equals constants, and the metric is actually a Calabi-Yau metric background, so the Ricci curvature vanishes. So in words, at the lowest order, we find an unwarped Calabi-Yau with constant dilaton as our background. With regard to the fluxes, the equations that the fluxes have to solve are the ones shown here on the bottom. And that just means that the fluxes are harmonic with respect to the background metric. And crucially, in this background, we do have AISD flux non-vanishing even at the lowest order. We can then proceed to the next order. I'm just flashing the equations here. The details are not too important, but I want to show the expressions nonetheless. So the first equation just generalizes the equation for the warp factor, while the next 3 equations actually take us beyond GKP. This is because the right-hand side now depends on G minus, and G minus 0 is 0 in the GKP background. But here, this is actually non-vanishing, so these equations become non-trivial. And furthermore, we have.
Sorry,
yes, please.
Can we go back one sec? You have on the previous slide. You had a. Sorry, I have kids in the background,
yes.
So there's some background noise. You have a G minus that you're turning on at lowest order, not including back reaction, presumably, at this order?
The back reaction comes at the next order, right? I mean, the back reaction is precisely captured by the next order equations.
So if I look at the supergravity equation of motion, there's some R mu nu equals double contraction of G's with some mu nu. So that equation is not yet solved, right? In the previous slide.
That the internal equation is solved, not the external one.
No, even the internal one would not be solved if you've turned on a flux on the internal space. You have some stress energy on the internal space.
Yeah, correct. But it is here in our expansion that enters into the next order equation. So as you see here in this equation. So this is the back reaction that you have on the metric background.
Okay, and the assumption is compact Calabi-Yau as a starting point, right?
Correct.
Yeah. Okay.
Compact, yes. Yeah.
So the claim is G minus, turning on a G minus is absorbable just into a warp factor.
Correct, yeah.
Okay, thank you.
You're welcome. Are there any more questions? Okay, if not, then let me proceed and just comment that these perturbed equations of motion are much simpler than a general system. It's a triangular system of Poisson equations. So these have particularly nice properties. And this generalizes an observation that has been made previously in expanding around ISD solutions by Liam and collaborators. And let me also stress that this analysis can be continued to any desired order in the expansion of 1 over C, but the first non-trivial order for the most part will suffice for the discussion today. So now let me tell you what we actually want to do with these expansions of the equations of motion. So let's first look at the effective action. So what we want to compute is the warped effective potential. And so here I'm flashing just effective action for the light degrees of freedom, which I call phi m, where we want to compute this potential V effective in terms of the light degrees of freedom. Let me note that if we wanted to compute the kinetic terms as well, this is much more involved. One has to change the ansatz for the background and so on and so forth. This has been studied in the past, and this is not what we're going to do today. So today we only focus on the potential itself. Now, to compute this potential, the first thing that we do is we plug our background into the 10-dimensional action to get an expression for the actual potential, and this is the expression that we find. But this is not quite yet what we're looking for, namely, this is a rather formal expression, and to evaluate this potential and link it to the effective potential just in terms of the light degrees of freedom, and not just in terms of the light degrees of freedom as well as all the KK modes, we have to choose the field profiles on which we want to evaluate this expression. So what do we actually want to achieve? So first, we want to identify what are the light degrees of freedom. We then also want to solve the equations of motion for the heavy KK modes, because these are the ones that we want to integrate out. And then upon integrating out these heavy KK modes, we want to determine the effective potential for the light fields. And to do that, let me illustrate that the procedure that we're using with a very simple toy model, just to set up the stage for what I'm about to do. So the toy model is as follows. We look at the d-dimensional theory for a single scalar with a source term rho. You compactify that theory on a product background with a 4-dimensional non-compact space and a small d-dimensional compact space. So the equations of motion factorize as such. And to solve the internal equations of motion, the best way to do that is by going into the Fourier space. So we're expanding all of our fields into Fourier modes along the compact space. And then we can derive the equations of motion for the Fourier modes phi I, as shown here, where in particular, let me note that the zero mode equation here, because the zero mode has a vanishing eigenvalue, is just rho 0 equal to 0, with rho 0 being the integral over the source itself. Okay. Now to compute the effective potential in this simple setup, one can go about this in two ways. Either you start from the action, compute the full potential in terms of all of your Fourier modes. You can then find the minimum for all the KK modes, but just finding the critical point of this effective potential, plug in the solution that you find, and thereby integrate out the KK modes. However, in practice, this is quite tricky to apply, because you need to know how to determine the full potential in the first place. But there's an alternative procedure where instead you first remove the zero mode from the d-dimensional equation of motion by here subtracting off the rho 0 from your corresponding Poisson equation. You then expand this equation in terms of your Fourier modes, which means that you only get an expression in terms of the heavy KK modes, which is then precisely what you want to solve, and that you can plug into your action and then compute the effective potential, which will leave the light degrees of freedom as a dynamical field. And so in practice, for our purposes, the second approach is much simpler because it's a very nice strategy where you don't have to explicitly determine the full potential in terms of the KK modes as well. Okay. So let me now illustrate how we go about this. So in the Type IIB context, we now want to apply this recipe of subtracting off the zero modes. So this works as follows. So here we have the equations of motion for the KK modes where we subtracted off, here highlighted in red, C phi and C tau. These are what I refer to as the zero modes, which are nothing but the integrals of the right-hand side of the original expressions. So this is the zero mode for phi, and this is the zero mode for tau. And let me also highlight that there's only a single zero mode for phi plus and phi minus due to the D3 tadpole cancellation condition. This actually relates to the two zero modes of these two fields, and so there's only a single zero mode that you have to consider. For the metric, this procedure is slightly more involved in the sense that first you have to figure out what are the zero modes. In the Calabi-Yau background, we know very well what these are. Namely, these are the scalar deformations and the complex structure deformations. And these you can then again subtract off from your equations of motion for the metric, where the zero modes are defined here in terms of the scalar parameters and here in terms of the Weyl-Peters symmetric and complex structure modular space. Okay. Now, with these zero modes in mind, what have we actually achieved? So what are the zero modes telling us? So these zero modes isolate for us the equations that have to be satisfied for the 4D fields to take on values at a critical point of the effective potential. So what I mean with that, solutions to the first order zero mode equations, meaning all the CMs set to zero, these solutions should correspond to the 4D fields in your 4D effective theory being at a critical point of your effective potential at leading order. Okay, so let me illustrate that explicitly, that the statement is actually true. To do that, you expand your fluxes in terms of harmonic forms. You can plug this into your expression for the zero modes, and after some algebra, you can express the zero modes in terms of your periods. So fair enough. This is just one part of the story. Now, this is what we want to match with a corresponding 4D calculation. The 4D calculation that we do is we choose the standard expression for W and K, meaning the Gukow-Witten superpotential as well as the leading order scalar potential. We do the same computation in the sense that we look at the 4D F-term potential and we compute its derivative in terms of the periods. And the expression that we find are shown here on the bottom. And if you remember the expression on the previous slide, which I'm sure you also have forgotten by now, so let me just summarize it here. So we find an exact match between the 4D calculation and the zero mode equations that we got from the 10D equations of motion, in the sense that the derivative of the leading order potential with respect to tau and the complex structure moduli is precisely proportional to the zero modes for these two fields, which means that critical points of the leading order potentials are indeed solutions to the zero mode equations where these zero modes vanish. And then, of course, similarly, you can compute the derivative with respect to the volume, which in our notation is just C, or proportional to C. And so this shows that a critical point for C only exists if this leading order potential vanishes, and otherwise there is a runaway to decompactification. And so to summarize, what we've shown with this calculation is that the leading order offshore potential can actually identify it with the GKP-like potential, even if G minus 0 is not equal to 0. Okay. Now, next, what we were actually interested in is going beyond the leading order. We want to go to subleading order. We want to estimate the correction that come from the back reaction to this background. So let me come back to my original expression for the offshore potential. And let us now try to compute the subleading order in our 1/c expansion. So the first two orders we've already looked at. These are kind of trivial. Now we want to go to order 1/c squared. At 1/c squared, the expression that you find is this expression here.
You have
now
about
to
5
evaluate.
minutes left. Sorry, you have about 5 minutes left.
Oh, all right. Thank you. Now to evaluate that expression, of course, in a perfect world, we would like to solve the equations of motion at that order fully analytically and that plug in the solution for phi plus minus 1, etc., etc. But this is hard. So what we do instead is we perform a parametric analysis and try to understand the parametric scaling of this correction to the potential. Let me actually skip this part here in the interest of time. So the parametric scaling that we set up is that we just say that G minus is proportional to epsilon, G plus is proportional to square root of n, the imaginary part of tau 0 we set to 1/gs. We can then use these parametric scalings to estimate the scaling of the equations of motion to first subleading order. So these are the scalings that you obtain. You can then use this expression and plug them back into the expression for the potential that I showed on the previous slide. And you estimate that the correction that you find scales as such, shown in the bottom, and then comparing this correction against the leading order term, you see that this correction is suppressed in the dilute flux regime where GSN is much smaller than C. Okay. Yeah, let me also skip this part, unfortunately. And now let us use these results that we have obtained here, so this parametric scaling result, and try to see what this is actually telling us about applications of this type of solutions to FTEM uplifting. So as I said in the beginning, the idea in FTEM uplifting is that you have some procedure to stabilize scalar moduli in an ADS minimum. And then you want to use the leading order potential coming from the AISD fluxes to uplift the solution to a de Sitter vacuum. And here, of course, the existence of such a minimum depends highly on the detailed stabilization mechanism. And I will comment on the most famous one, LVS and KKLT, in just a second. But we have to be very careful here, namely that there can be additional corrections that could spoil, in principle, such an uplift. And we identified two sources of corrections. The first corresponding to back reaction effects from warping, which we just estimated, so this delta V effective. But then there can be additional corrections that come from mixing terms between the AISD fluxes and additional quantum corrections. Indeed, if we want to stabilize scalar moduli, we typically have to take into account further quantum effects to the scalar potential and the superpotential. So for example, well-known sources are ED3 instantons, which contribute with e to the minus t to the superpotential. And so these mixing terms between delta K and delta W, as well as linear factors in G minus, are quite dangerous for the stability of the uplift itself. And of course, it's not sufficient to just look at the potential itself. You also need to compute the corrections to the masses. In particular, it is well known that in these setups, there's always a light complex structure modulus. This goes back to a famous paper by Denef and Douglas. And so this light complex structure modulus can be quite affected by these additional correction terms. And so the parametric stability condition that we check is shown here on the bottom, where we just check that the mass scale, as shown here, is larger than the contributions that come to the Hessian from the corrections to the potential itself. So for delta V effective, what does that actually imply? As I said before, the contribution to the potential is negligible as long as GSN is smaller than the volume to the power 2/3. However, the stability condition depends actually on the detailed stabilization mechanism, in the sense that, so here the condition that we looked at depends on epsilon, and this epsilon depends on the type of Kähler moduli stabilization procedure that you're using. So let me make this more specific. So in LVS, epsilon has to scale with W0 and 1 over volume to the 1/2 in order to have a successful uplift. While in KKLT, epsilon has to scale like W0. You can then estimate what are the corrections coming from the mixing terms and potential. In the LVS case, these are suppressed only by volume to the -1/6, whereas in KKLT by roughly the volume to the power 2/3. So in KKLT, it seems actually much better. But it turns out, if you now look at the stability condition for the Hessian, you will notice that while again in the LVS case, the suppression is with the volume to the -1/6, in the KKLT case, the minimum could be easily destabilized because the condition that you find here, while it naively looks like it's sufficiently suppressed with the volume, because W0 is also relatively small, you can check, for example, in a 1 modulus case, this seems to be quite dangerous because it scales exponentially with the volume modulus. And so this tells you that, at least in the KKLT case, there might be a worry that these corrections could actually spoil the uplift altogether. And so with that, let me conclude. So we obtained a 4D off-shell effective potential for the light fields. We integrated out all the heavy KK modes in the 1/c expansion and estimated the size of the leading corrections from warping, and then applied these results to F-term uplifting for AISD fluxes. And so with that, let me thank all of you for your attention.
Right, let's thank the speaker for a very nice talk. Is there any question from the audience? Saf?
Guys, thank you for the talk. I'm a little bit confused about the claim. Is the claim that if you turn on G minus, that you have a supergravity solution that's static?
No, that's not static, no. As I said, so, oh, sorry, let me go back. Well, let's go here. It would only be a static solution if you actually solve all of these equations, so these zero mode equations, but sorry, that's the wrong slide. This slide, this is what I want to show you. And clearly there's, for example, always one equation that you cannot solve, which is the one for the volume. Indeed. And so that gives you runway.
Okay, so you want a cosmology as your space-time at the end of the day, or?
Yes.
Okay. Okay. I mean, I guess maybe I should ask differently. What's the end goal of turning on G minus? You can take any compact space, turn on any kind of flux that you want, and it will run away to do something time dependent. What's special about this story?
Well, so I would say this is just the first step in a big analysis that one needs to do, in the sense that one has to take into account. So this goes back to this analysis here. One would need to take into account these additional terms to the equations of motion that actually lets you stabilize all of your fields, and then you can have a chance of having a static solution.
Okay, so I mean, this goes back to a fundamental, I think, misunderstanding, which is also a problem with KKLT, this GKP. Your starting point is not a solution. Your leading quantum corrections will not be. Do you want these to be perturbative corrections or non-perturbative? Because you talked about D3 instantons again.
Could be anything, but including those at the level of the handy equations of motion is of course highly complicated. So I wouldn't know if that's even feasible.
Yeah, it's not really even feasible in the current constructions, let alone one wave even more brutally broken the fact that it's not a solution. I mean, any of these non-SUSY flux spaces are automatically not solutions.
But again, so the first order, what we do is we're looking at the off-shell description here. We're not solving all of the equations of motion, right?
No,
we are only solving for the heavy KK modes.
Yeah, you can go off-shell, right? So yes. to the extent that one can try to KK reduce on this background, get some effective theory, and hope that this will reverse engineer back to some 10D solution. The real issue is, can one ever reliably compute things like non-perturbative quantum corrections to this off-shell configuration? That's very hard.
That's I totally agree. That's very hard, and that's not the question that we have addressed here, for sure.
We just have to interrupt. In the interest of time, shall we move this interesting discussion after the talks?
That sounds good. Thank you.
Thank you.
Okay, thanks.
All right, Bruno.